All right, let's talk about one of the most important and maybe most misunderstood topics in getting large language models to actually work in the real world: quantization. Today, we're going to cut through all the noise and really dig into what's happening in production, what the real make-or-break challenges are, and where we're headed next. So let's jump right in.
You know, this statement right here, it gets to the heart of a massive misconception. It's so easy to think that the biggest, baddest GPUs with the most raw computing power, we call that flops, right, are the secret to making LLMs work. But in the trenches, in actual production systems, that's just not the real story.
So what's really going on? The real demons are things like memory bandwidth, that's how fast you can shovel data into the processor. It's VRAM ceilings, the hard physical limit of your GPU's memory. And it's the cold, hard cache and energy it costs to generate every single token. These are the walls that teams are smashing into, and this is the problem that quantization is meant to solve.
So here's our game plan. First, we're going to nail down what that real bottleneck is. Then, we'll talk about why quantitation is the answer to that specific problem. We'll look at what's actually being used out in the wild, dive into the really tough challenges that the pros are wrestling with, and then we'll peek into the future of precision.
Okay, first things first, let's get one thing straight right from the get-go. When you're deploying these massive models, the thing that slows you down the most isn't how fast you can crunch numbers. It's all about memory.
So, why is that? Well, imagine your GPU's tensor cores are these incredibly fast workers, just ready to go. The problem is, the conveyor belt that brings them the data, the model's weights, is just way too slow. That slow conveyor belt is your memory bandwidth. It means your super expensive, super powerful cores are literally just sitting there, twiddling their thumbs, waiting for data. And you know what makes it even worse? For longer conversations, the model's short-term memory, something called the KV cache, just balloons in size, eating up your precious VRAM like there's no tomorrow.
And that brings us to what I think is the most important idea in this whole explainer. We have to stop thinking about quantization as just a clever math trick to make models smaller. We need to see it for what it really is in a production environment.
You've got to make this mental shift. The common view, that quantization is just about shrinking a file on your hard drive, it totally misses the point. The reality is, it's a systems-level strategy. It's about fundamentally attacking that memory bottleneck when the model is live and running, dealing with data in motion.
So what are we actually doing when we quantize? We're taking the numbers inside the model, its weights, and we're representing them with fewer bits. Instead of a big, clunky 16-bit number, we use a sleek 8-bit or even a tiny 4-bit number. The less data you have to move, the less pressure you put on that memory conveyor belt, and the faster everything gets. It's as simple as that.
And the payoff here? Oh, it is huge. When you fix that memory problem, everything else just gets better. You can process more user requests at the same time in bigger batches. Each GPU pumps up more tokens per second, which means your throughput goes way up, and that directly translates to lower costs and way better energy efficiency. The speedup is a direct result of saving memory.
Okay, so that's the why. But how do teams actually do this in the real world? Well, it mostly boils down to two main approaches. One is called post-training quantization, or PTQ, and the other is quantization-aware training, or QAT.
Let's break this down. Think of post-training quantization, or PTQ, as the reliable workhorse. It's what you do when you just have the final model, there's no time or money for retraining, and you need it live like yesterday. It's pretty much the industry standard and works great for models up to around 13 billion parameters. Now, on the other side, you have quantization-aware training. This is the expensive, high-maintenance option. You use it when you control the whole training pipeline and accuracy is non-negotiable, maybe for a model on your phone. But because it's so expensive, you almost never see it used for those giant cutting-edge models.
Now here's a super important detail about PTQ. You'll hear about tools like GPTQ, AWAQ, and SmoothQuant. But as models get really big, say over 30 billion parameters, you can't just apply these tools blindly. You have to give them a little taste of real data first. This calibration data helps the algorithm make much smarter choices about how to shrink the numbers without accidentally throwing away the important stuff.
Okay, now we're getting to the really fun part. We're moving past the basics and into the deep, thorny problems that separate a simple quantized model from something that is truly stable, reliable, and production-ready.
So here's a perfect example of one of those thorny problems: per tensor versus per channel quantization. The simple, kind of lazy way is per tensor. You look at a whole grid of numbers, find the biggest and smallest, and create one size-fits-all scale. But what if one of those numbers is a massive outlier? Well, it completely warps the scale, and all the other, more subtle numbers get squished together, losing all their detail. The smarter, tailored approach is per channel. It gives each row its own custom scale. This does a much better job of preserving the important information, and that directly translates to better reasoning.
But here's the thing. We've only been talking about half the story. The model's weights are static, right? They're set in stone after training. But what about the numbers that are actually flying around inside the model while it's thinking? What about the activations?
This, right here, is the real frontier of difficulty. Activations are a moving target. They change with every single input you give the model. And what the experts have found is that when a model is doing some really deep thinking, the range of these activation values just explodes. When you try to quantize that, you crush all the nuance, and the model's ability to follow a long chain of thought just falls apart.
So let's walk through exactly how this damage happens, especially when you get aggressive with something like 4-bit quantization. First, a few huge outlier values pop up in those activations. They completely dominate the scaling factor. Second, because of that, all the other normal, well-behaved values get crammed into a tiny little range, basically losing all their resolution. And third, that loss of precision isn't just random noise. It systematically breaks the model's ability to reason.
So, what are the smartest folks in the field doing about this? Well, the cutting-edge techniques you hear about, like AWQ and 𝗏𝗂Quant, are all designed to fight this exact outlier problem. They're basically trying to either act like bodyguards for the most important values, protecting them from getting squished, or they do some clever math to redistribute the spikiness to parts of the model where it's easier to handle.
All of this brings us to the future. So, given these really complex trade-offs, how do we even know if we're doing a good job? And what are the next big ideas that are going to push this whole field forward? For a long time, everybody just used a simple metric called perplexity. But we know now that's not good enough. A modern evaluation has to use benchmarks like these. GSMA-K checks if the model can still do hard math. MMLU sees if it's forgotten basic facts. Truthful QA tests if it's started to make things up more. And Longbench directly attacks that weak spot we talked about, its performance on really long tasks. And this right here is probably the most critical takeaway for anyone working on this stuff. The model's ability to reason breaks first. It will start failing on those complex benchmarks way before that old perplexity score even starts to twitch. Perplexity, it turns out, is a lagging indicator. It tells you about the crash after it's already happened. So where is the real innovation headed? It's not just about another 4-bit model. It's about much deeper, cooler ideas. I mean, think about models that can change their own precision on the fly, or algorithms that can intelligently give more bits to the most important parts of the model's brain. We're talking about designing the hardware and the software together from the ground up, and finally solving that exploding KV cache problem. This is the real cutting edge.
And that really is the perfect way to sum it all up. The goalposts have moved. Just getting a 4-bit model to run, that's not the win anymore. The true breakthrough, the real holy grail for this entire field, is getting all that amazing efficiency without sacrificing the model's incredible ability to reason. That is the challenge, and that's the future we're all working towards. Thanks for tuning in.